So the nature of the fluorescence and phosphorescence process changes the, the way that we think about measuring them for the better, in that it actually gives us an edge on measuring emission of photons compared with simply measuring absorbance. So what I have is a really simplified version of an instrument diagram for a fluorescence measurement, where you have your lamp, some broadband source, and that actually is in direct line with your sample and blank cuvette. And this may be a dual beam setup with a chopper, and I'm just sort of reducing that. And that's not important right now because that's just a separate issue that we've already talked about. What I'm talking about is that now what we do is actually change and reposition the wavelength selector, in this case the monochromator, and the detector, such that they're roughly 90 degrees out of phase with where they would normally be. Because normally we would have this, the light path, and then hit the detector, and that would be an absorbance geometry. So this would be an absorbance detector. And the idea here is, because of the nature of fluorescence, right? You have an absorbance step that occurs with a photon that is shorter in wavelength. I should say that this is, I'm comparing wavelength here, shorter in wavelength than the light that gets emitted through fluorescence. And since they're distinctly different from each other, what's nice is that instead of having the same light, all of the light that's moving in towards the detector, and trying to measure a small difference in signal relative to our original light, which is what we do when we measure I versus I naught. We're measuring a small difference if you have a very small amount of analyte. In the fluorescence geometry, because it's emitting a distinctly different frequency, completely different than the source light, and it's emitting those things rather than simply absorbing them, think about all the molecules inside here that are absorbing this light and then proceeding through a fluorescence decay mechanism. They're emitting light isotropically in all directions. Right? So it doesn't matter where we place our detector, whereas absorbance, it's important, it has to be directly in line with the light source. So we have this isotropic emission of a light frequency that's different than our initial source, so that allows us to decouple our detected frequency from our input frequency of light. And what that, people talk about, the sort of benefits of that are that you're essentially measuring a signal, a pure signal, on a completely dark background, rather than measuring a small change in signal on a very bright background. And so it's much easier to see a small signal on a dark background than it is a small signal on a light background, which is the sort of comparison to absorbance. In that case, fluorescence becomes far more sensitive than absorbance measurements, in so much that right now we can do single molecule fluorescence experiments if they're designed correctly, meaning we can measure the fluorescence on a single molecule, which we couldn't even come remotely close. We could probably measure absorbance changes on like maybe 10 to the 18th number of molecules, compared to fluorescence, which we could literally measure 10 to the 0. We could measure one single molecule. So huge, huge, huge change in sensitivity. An analogy that I like to think about in measuring a fluorescence signal in this type of geometry is sort of akin to measure or seeing cell phone cameras like this, like the image that I'm showing you here, on a completely dark background in a dark stadium, compared with trying to see those same cell phone cameras in a completely lit stadium, which is the same. The lit stadium analogy is trying to measure that signal against a background of light, which would be the I naught. Whereas right now, this would be an analogy of fluorescence. And even in, you have these giant stadiums that maybe hold 100,000 humans. If you're standing down in the center of that stadium, if one of those 100,000 people turned their camera phone on or their light on, you would be able to see it, which is sort of the analogy with fluorescence. Whereas in the daytime, no idea. You would never be able to see that. Or if everybody had their camera on and you were trying to differentiate between one person turning it off or on, which would really be the analogy for absorbance, that's much harder to do on a small level. So this is why we measure absorbance in this way. So what does a fluorescence spectrum actually look like? I showed you what an absorbance spectrum looks like. And so if we think about it from a Jablonski diagram perspective, you essentially have, let's use red. You have everything in the ground state, which is this state here. And then as you shine white light on this thing, whatever this molecule is, you get excitation in all these different vibrationally excited states. And what happens with fluorescence in each case is each one of these excited states, wherever it ends up here, every single one of them, remember, is going to go through that non-radiative transfer process where we denoted it by a squiggle line, where it's going to relax through some sort of vibrational friction with other molecules. And so they're all going to start then from this same point when they fluoresce, and that's the emission step here. And so as they emit, then they, even though they absorbed at all of these different frequencies, which is why you have the black spectrum here, you see all of the different photon energies that are absorbed, which correspond to the different lengths and arrows. In the emission state, they're all starting from the same point, and they emit down to essentially like the mirror images of the vibrational levels, but from the ground state. So this would be the excited state and its corresponding vibrational levels. This is the ground state and its corresponding vibrational levels. And since everything can relax from the same point, some of those will relax to the highest vibrational excited state, some will relax to the next highest, and some will relax all the way down to the ground state. And so in each case, those are different lengths of photons, different wavelengths. And so what we get is something that's pretty similar to a mirror image. And so if you were to overlay the absorbance spectrum and the fluorescence spectrum, you would end up with features that very similarly mirror each other, and that's because the vibrational levels mirror each other in the ground and the excited states, but you're seeing the opposite of that. You're seeing the emission of that versus the absorbance of that. And what's being shown here, normally you don't see these on the same spectrum. Normally you're recording absorbance or you're recording fluorescence because the geometry of the instrument's different. And so it's important to know that, but you could measure both. And most fluorimeters are set up to actually have, you have your light source, and then you have your cuvette here, and then many of them have a detector right here, which can be used for absorbance measurements, where it's directly through the sample like normal, and then many of them have a separate detector down here for fluorescence. So you could actually do both. You can see that these two spectra that are overlaid with each other, one was measured at roughly a micromolar concentration, and one was at like 10 picomolar, and you get roughly the same intensity for these two things simply based on the geometry of the process. So it's important to think about the sort of symmetry in what a fluorescent spectrum looks like. You're not getting, simply a single band of fluorescence. You're getting essentially like an imprint of all of the vibrational states in that molecule, at least within that first electronic excitation. If it's not clear, there are many electronic excitations. I mentioned this in a previous video. So whatever you see here, imagine that there's then on top of this, another set of bands of vibrational levels up here, which would be the n equals 3 state. And so you can sort of end up having like these repeating symmetrical structures if you add more and more energy. Of course, in this case, this would be way out in the non-visible land to get something to excite to such a high energy state, which is why you don't usually see more than one set of excitations in a UV-Vis spectrum.